And to kind of start this process off, we're going to lead with this example. And we're going to stick with this example for a little bit in today's lesson, and then kind of move forward and go back to the caffeine experiment, and then do another experiment at the end. So this example is SAT in schools. So many students enroll in prep courses to improve their SAT scores. 20 students who have taken the SAT once volunteered to participate in an experiment comparing an online and a classroom prep course. So I have two different classes they can take for SAT prep. One's online, one's a classroom class. So using our knowledge of completely randomized experimental design, let's design a completely randomized design to compare these two SAT prep courses. What would I do first?
Put every 20 students' name in a hat.
Yes, 20 students, names in a hat, right? This is the easiest way to randomize. I heard Elijah, I think, or yeah, you said randomize? Yeah. So I need to randomize. I need to put these 20 people into groups of 10, right? 10 students over here, 10 students over here, okay? I would always say put the names of those students in a hat, grab out 10 of them. Those 10, first 10 I get go to one of the classes. You have to specify. So I would say the first 10 go to the online class. The 10 left in the hat go to the classroom class. What do we have to do next? After we get them into the classes?
Give them different courses.
Administer the course, right? We have to administer whatever that class is. Then what? They have to take the SAT, right? All of the students in both classes take the SAT. And then what do? Get the results, find the average of both classes, and then compare the results.
Wait, what does it
Right.
mean to administer the class?
So basically, they go through the class. They go through the SAT class. They go through the online SAT or the classroom SAT class. Okay, so one of the biggest things that students miss in this type of problem is they forget to compare the results to the other classes or the other groups. So make sure we get all the results, compare them with what we're looking at. Okay, so among the 20 volunteers, 10 are in pre-calculus, 6 are in algebra 2, and 4 are in geometry. What problem does this cause?
They all write down
Different levels of math, right? So their SAT proficiency, I guess, would probably be different. Okay, the pre-cal students probably are working at a higher level than the geometry students. Okay, now, what's a bigger issue in that? Because randomly, I should be getting us two similar groups, right, Sam? Two similar groups if I just randomly assign from a hat.
You could get all the lower ones. I mean, there's possibility all the lower ones could be in one classroom.
For sure. It's possible that I get all of the lower ones in one group, all of the higher ones in one group, with just a simple random sample, or just pulling names out of a hat, right? That's the issue. So how can we address that problem? Everybody says stratify, right? We have my pre-calculus kids. I have 10 of them. Do an SRS of 5 and 5. 5 in one group, 5 in the other class. Do the same thing with geometry. Do the same thing with algebra 2. Okay? Split them in half by doing an SRS. Okay? Now, when we're sampling, that's called stratified random sampling. Okay? Stratified random sampling. When we have an experiment, we call it something different. Now, listen, there is a distinction between an experiment and a sample. Okay? With an experiment, we normally are dealing with volunteers. We're normally not dealing with a sample from a population. Think about it. If I was doing an experiment with GAC's high school student body, and I was trying to get a random sample from that student body, I would have to make sure that everybody in my population was willing to be a part of my experiment. Normally that doesn't happen. Normally what you do is you say, okay, I need volunteers for an experiment. So we have people that just volunteer for this experiment, which we have here. Okay? So we call it something a little bit different than sampling because we aren't taking something from the big population. We just have already kind of a sample, but it's not really even a sample because it's just volunteers. Does that make sense? So that's why we call it something different. And that different thing is called blocking. Okay? It's called blocking. So when I block, I'm doing the same thing as when I stratify. When I block, I'm doing the same thing as when I stratify. I'm taking groups that have common variables that might affect the response variable. Yes, ma'am?
So is number 2 blocking?
Yeah, number 2 is how we can address the problem. We'll be blocking the variable of what class they're in, what math class they're in. So I have these results here where I blocked. I have 5 pre-calculus students in each class, 3 algebra 2 students in each class, and 2 geometry students in each class, and I have the results. This number is the improvement from one SAT to the next after the class was admitted. Okay? So, it asks us to make dot plots to compare the improvements of the students in the online course and the improvements of the students in the classroom course. So, when I'm doing dot plots, we've done dot plots before. When I'm trying to compare 2 dot plots, I want to make sure that my scale is the same. So, I go from 0 improvement down here to 100. So, I need 2 dot plots. Okay? Or no. Aren't sure. All right, let's see here. Work. Okay. It should be. Yeah, that would be good. All right, so let's just do it on here. Let's see what I got. All right. Pretty bad. All right, so 0, 10. That's too far. 20, 30, 40, 50, 60, 70, 80, 90, 100. All right. No. I'm going to think smarter, not harder. How about that? Even though that's a terrible one, we'll live with it. Okay. So, I have my online, and I have my classroom. Okay? So, when I'm going here, I need to look at the improvement scores. So, I'll work my way from the bottom. Let's do the online first. I have 230, so we go here. Not terrible. Could be worse, could be better. Online, I have a 40, a 50, and a 60. So 40, 50. There's got to be a better way, but we're just going with it. We're going with it. We're going with it. 300s and a 90 and 2 90s. 300s. Oh no. I feel like I'm concentrating so hard. All right. Awesome. So there's online. Classroom, do the same thing. I have a 0 and a 20. All right. This is taking so long. 30, 40, 20.
Do the big dot.
Just do a big dot.
I know. I'm already committed. I feel like I'm already just here. We're just gonna sit here in it. I know. It would be so much faster. There's a lot of things that I would do differently about my life. This is one of them. 80, 80, 80, and then 2 70s. All right. Almost done. All right, so. Love that. Okay, so based on the dot plots, does there appear to be convincing evidence that the online course is better? So one thing that I want to make sure that we're aware of is this word convincing evidence and understand what that means. So convincing evidence ties to statistical significance. Okay? If something has statistical significance, it means that I have convincing evidence for something to have happened, right? So yesterday, had we found convincing evidence about the distracted driving or statistical significance. We would have said we have convincing evidence that cell phones are more distracting than passengers. Talking on a cell phone is more distracting than a passenger. We have convincing evidence. We didn't have convincing evidence because there was not statistical significance. Okay, so that word ties with statistical significance. Okay, so do I, based on just the dot plots, we don't have any numbers, based on the dot plots, do you think we have convincing evidence that the online course is better? Not really. Not without a shadow of a doubt, right? It does look like the average improvement was better in the online course, but it doesn't seem like it's that much of a difference. Does that make sense? Okay. So, what if we have dot plots that are separated by class, where my symbols in my dot plot is by class, so those squares are my geometry people. My geometry people. Those circles are my algebra 2 people, and those triangles are my pre-cal people. When I look at that, it looks like I have more of a difference. Like every single class, there was more improvement in the online class. Okay? How
do you control what variable matters? Like, you can say something's statistically significant, but like you could take a stat of anything, right? You could say the online class had 100% more.
Right. So we have to. That's a good question. We have to decide what variable we're looking for, or what statistic we're looking for at the beginning. What are we looking for at the beginning? So then at the end, we don't like kind of skew what's going on. Does that make sense? To our liking, if that makes sense. So we're looking at average improvement for each class. So is the average improvement better? That's what we're looking for. Yeah.
So in number 3,
Yeah.
they did an SRS of.
No, number 3 is blocking still. It's just visually displaying those graphs a little bit differently.
So they did like stratify and how they took a little
Right.
bit from each level.
Yep.
But in number 4, they didn't.
No, number 4 we still did. So number 3 and number 4, this is just awful. Number 3 and number 4, this dot plot and this dot plot are the same. The only difference is in this dot plot, I've kind of symbolized the different classes to make it easier for me to see the difference within each class, right? Within each math level, I should say, not class. Okay. The triangle is the pre-cal students. The circles are the algebra 2 students, and the squares are the geometry students, which are the same dots and X's that we have here. It's just we can't really see those. So within each level, we can see the differences more. So how can we use the information that we see here to account for the variability created? We block. We block by class level. We want to make sure that there's an equal amount of students in each group. So what is blocking? On a more formal level, blocking in experiments is similar to stratification and sampling. Blocking accounts for a source of variability. Not every source of variability, just the source of variability that comes from the variable that we are looking for or looking at. So when we block, we do it so that we can increase our chances of finding convincing evidence. Okay. Now, how do we choose blocks? Blocks can be chosen just like strata, okay? But we want to make sure that we choose the thing that we think affects the response the most, okay? So in this case, we probably would think that the class level affected the response the most, okay? And we do not form these at random. All right, going back to the caffeine experiment. What are some things, some variables that we can block for in the caffeine experiment? Remember, caffeine, I had 2 groups, caffeine, no caffeine. What are some confounding variables that we can block in that caffeine experiment? Male or female, right? Age?
Physical That's hard to
tolerance
quantify.
to caffeine.
What's that?
If you get, well, if the caffeine can affect you.
Fitness.
That's kind of hard to quantify.
Yeah, that's
Okay, what's that?
Ooh, BMI.
Weight.
BMI.
Weight's a good one. What else?
BMI.
BMI is a great one. Similar to weight. What else?
Average, like,
Okay, caffeine intake. If you drink a lot of caffeine or not. Another thing could be how much you exercise. Another could be your resting heart rate. We could block by resting heart rate. Okay, those are all good variables. Now, in general, we determine the best variable that we think affects the response the most. Because in the caffeine experiment, could we block for every single variable? We could, but should we? Probably not. Okay? Probably not. It would take, you'd have to have this huge big sample. We'd have so many different groups, so many blocks. It would just be crazy. Yeah.
Is male and female one or is that
Yeah, that's a good one. Yeah. Elijah said that. So far we've talked about two different types of design, experimental design, and you need to know the different types of experimental design. The first one is a completely randomized design. That was an SRS. We're putting two groups, and we're randomly assigning them to those two groups, or however many groups we have. The second one is a randomized block design. A randomized block design where we are taking a variable or multiple variables and blocking them and putting them people into still the same two groups, but in a different way. Okay? Randomized block. All right, so we have this example about microwave popcorn. Popcorn lover wants to know if it is better to use the popcorn button on her microwave oven or use the amount of time recommended on the bag of popcorn. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. She goes to the store and buys 10 bags of each of the 4 different varieties of microwave popcorn. Movie butter, light butter, natural, which is gross, and kettle corn, for a total of 40 bags. If you eat just popcorn, that's fine. Go for it. That's just, home style is my favorite. If anybody else. Yeah?
Sure.
Okay. I just don't like it. I don't feel like that's popcorn, though. It doesn't feel like popcorn.
Light butter or kettle
Yeah.
corn.
I guess.
It's like Publix brand or
Okay.
Kellogg.
Gotcha. All right. So, explain why a randomized block experiment design would be better or more preferable to a completely randomized design. Okay. What does the different types have an effect on the response? Okay, it could pop differently. Kettle corn might pop faster or slower than the movie butter. So interesting. One of the students in the last class asked, "How do they get the butter inside the kernel?" They just put the butter on like the bag in the bag, right? And it just gets on the popcorn after it's popped. It's a pretty interesting conversation. Anyways,
It's actually grown with butter inside.
It is a special type of popcorn. So this is why I said you don't have to write down everything that I wrote. This is also online. But I said a completely randomized design ignores the difference between the 4 types of popcorn, which will probably result in a lot of variability in the number of unpopped kernels for both treatments. A randomized block design considers each variety separately, and it allows us to account for the variability in the number of unpopped kernels created by the difference in varieties. So there's different popcorns that could pop differently, and that's really the biggest issue. And the statistical word that we'll use there is it creates less variability, which is what we want.
Could that be a way of determining the cause for the difference in the salt?
For sure, it gets closer to us determining if one bag causes more unpopped kernels or not. Yeah, for sure. All right, so outline a randomized block design for this experiment. What would I do?
Separate each variety.
So each variety, I have to separate them and do what with those bags?
5 with microwave and 5 with bag recommended.
How do I do that? Do I just grab 5? SRS? How do I do an SRS? Number 'em.
Yeah, there's not names.
I can name each bag of popcorn, put those names in a hat. No. I would number each popcorn bag 1 through 10 in each group. I have to say that. Okay? Just because I know that doesn't mean the person reading knows that. Okay? So number each bag of popcorn 1 to 10 in each type. And randomly choose 5 numbers from each type. The 5 numbers that we randomly choose, we're going to use the popcorn button with those bags. And then we're going to use the time recommended on the bag for the other 5 in each group.
Why does it matter that they're all the same bags? Why does it matter that you randomly choose the bag?
It's a good question. It really is adding that layer of like I don't have any bias. Because what if like I grab 10 bags of popcorn straight from the shelf, and maybe the top 5 bags are just a little bit different than the bottom 5 bags in the way that they were made. You never know, so we want to randomize that just to make sure that they are similar as possible, to kind of take away that even chance that they could be different. I know it's kind of like semantics, but if I'm going to a popcorn facility, the same number of popcorn kernels are not never in the same in every bag. It's just not possible, right? So that's kind of to take away that process. Okay. Next thing I have to do, I have to pop the bags of popcorn and count the number of unpopped kernels and compare those 2 groups together to see which one has less unpopped kernels. Okay. And then I would be able to decide I'm going to use the popcorn button or the number of minutes. I prefer popping my popcorn on the stove. I think it is just better.
Yeah. Wouldn't
Like you get just kernel, you buy like a whole thing of kernels, pour them in the.
wouldn't this just lead to whichever one is longer, like popping more kernels?
Maybe, I don't know. Somebody we talked about burnt popcorn too.
Yeah.
So like you keep doing it, it's burnt popcorn. But it's not like we're putting like 10 minutes on the thing and just letting it all pop, right? It's what is recommended or the popcorn button on your microwave. All right, so last thing that we're going to talk about. So we have 2 different types of experimental design. Completely randomized block. We're going to talk about one more. And this is the most precise. It's a matched pairs design. A matched pairs design. So what is a matched pairs design? Can't use that today. It was working earlier. So a matched pairs design are when the blocks only include 2 experimental units. When the blocks only include 2 experimental units. Okay? Those 2 units can be a variety of different things. The first one, they could be 2 similar people. So let's go back to the caffeine experiment. And I wanted to make sure that I have the most similar groups possible. I'm going to probably block by age and gender and weight. And so I can try and get 2 people together as similar as possible. And what I do, I randomly assign one person to the caffeine group, one person to the other group. And I do that for every pair that I have. So here's an example. A girl in my class 2 years ago decided that she wanted to do her second semester project and she wanted to do a matched pairs design. She wanted to see if when taking a test or a quiz or some sort of assessment, how the students did if they had pressure versus no pressure. Okay? So the pressure group, and this was in my Honors Algebra 1 class that she used as the experiment. So the pressure group, I told them they had a limited time to do the quiz and that it was for a grade. And I bared down on them. It was a lot of pressure. And they were little 8th graders, so they were really scared. Okay? I felt kind of bad. So I think one of them cried. But it's okay. Afterwards, because she did bad on the quiz. The second group came in, no pressure. Said, you have unlimited time to do this quiz. It's not going to be for a grade. Okay, no pressure at all. take it. I just want to see how you guys are doing. Okay? So those are the two groups. But how did we make those groups? We ranked my students in terms of test score, how they do on tests. And we paired the top two together, randomly assigned one of those people to one group, the other one to the other group. Did that for every pair. So down the road, 1 and 2 were together, 3 and 4, 5 and 6, 7 and 8. Okay? Randomly assigned them. Group 1 with the pressure did awful. Group 2 without the pressure did awesome. Same test. I gave them the exact same quiz. It was like a 10-question quiz. Two different groups, same level in each group, but one group clearly did better. So she did a really good job of seeing that there was a significant result there by making sure that the groups were as similar as possible. It was as close to as the same as you can with this matched pairs.
So you got first best from each group, and the second best. So that's a pair. Second best pair.
So
third
number
best pair.
1 and number 2 test scores in my class, they were a pair.
But those were stratified by group.
They were paired by their test score. So the top 2 were paired together, and then I randomly assigned one of them to the pressure group, one of them to the non-pressure group. Or she did. I didn't do it.
But they were in classes, right?
They were in the same class together. It was all in the same class. So what I did, I like the pressure group, I took them out in the hall and said, you guys go out in the hall or whatever. And like the non-pressure group stayed in my classroom and took the quiz. And then the other group went out, next group came back in. I think I did the pressure group first. Because like they were like walking out the thing and they were like so scared. They were like, this is going to hurt my grade. You know, you're in 8th grade. Everything's scary. Okay?
Which group went first?
The pressure group went first. They walked out the door and they were like telling these kids, they were like, oh my gosh, that was so hard. And they came in and like it was really easy. So another way that I can do matched pairs designs is the same person and different parts of the body. Same person, different parts of the body. So how does that work? There's an AP question. We might do this question. So maybe, listen, there is a new glove coming out for gymnasts. And this new glove is supposed to increase the lifetime of the glove, right? It has a better wear. Okay? So I can use matched pairs design, but I can use the same person but 2 different hands. So I can randomly assign the new glove to one hand and the old glove to the other hand. Okay, why would that be helpful? Different gymnasts might work harder. Okay, why do I have to randomize which hand it's on? One hand might be more dominant than the other. Okay, so that's a great way to use matched pairs design to see the best. That's actually as close as we can get.
Probably need to do. Probably have to block by dominant hand as well.
Yeah, somebody Owen talked about that in third period about how like what if all of the dominant hand people got the new glove on their dominant hand. We can probably figure out a way to make sure that happens, but randomizing that kind of hopefully eliminates that enough if we do enough people. Okay. And then another thing we can do, same person, different day. You can be your own pair. Okay, so for example, if I wanted to see if testing while distracting affected my results, I could take 2 similar tests or 2 similar quizzes, one in a distraction-free environment, the other one in a distracting environment, whatever that would look like. Okay, but I would probably have to do that on like different days or with a rest time in between or something along those lines. But I would also have to randomize which treatment goes first. Yeah.
Wait, I'm a little confused how blocks are used, like with matched pairs, like how like the definition.
Matched pairs, what you are trying to do is you're trying to get the pair to be as similar as possible. You are literally like pairing them together. There is no random in the pair. The randomness comes from how we assign the treatment. Okay, which group they're in, or which treatment I do first. Okay, that make sense? Matched pairs. That's the last experimental design that we have.